Okay, two circles intersect. This one's got a diagram, so this is good. Two circles intersect at A and B. Straight lines PQ, good. Meet at A. One thing to note when they have drawn this, because you might come across some questions where they're going to ask you to draw two circles intersecting. Don't draw the circles to be the same size. You can see the one on the left is slightly bigger than the one on the right. Again, means that you don't assume things that might not be in play. All right, show that angle XBP. So XBP, we're going to connect to those. So we want this angle here. We want to show that is equal to YBQ. So hopefully you were able to do that. Have a look. And one of the tips is use your hand and cover up the right hand circle so you can just see the left hand side. And hopefully what you can see there is we've got angles subtended by the same arc. All right. And then you're trying to get to this angle here, but nothing's going on there. But what you do notice is that you've got vertically opposite angles here. Pardon me. And then you've got angles subtended by the same arc again. So that one I'm not going to write up. I think you could do that your good self. All right, let's have a look at now 9. And again, I didn't say it for the start of question 8, but again, all of these questions, I'm assuming that you have already had a go. All right, we've got a triangle inscribed in a circle, AB equals AC. All right, so let's draw our circle. A little bit wobbly, but it'll do. It's an isosceles triangle because AB equals AC. So we've got our isos, make it look like an isos, maybe not so much an equilateral triangle, but you know. ABC, make sure they are equal to each other. The bisector of angle AC meets the tangent from A. All right, so we've got a tangent from A, once again, right tangent, because that makes your eye go to certain theorems that have got the tangent involved. Meets an A, prove that AD, oh hang on, the bisector of ACB. So we've got a line bisecting, goes through and meets there at D. So because it bisects, if that's alpha, this is alpha, okay? Prove that AD and BC, oh dear, I don't look at on my diagram, but that's probably because my tangent was a bit dodgy. Prove that they are parallel. So now we're asking ourselves, how do we prove that two lines are parallel? So if we can prove that those angles are the same, then they have to be parallel. So the converse going backwards. And of course we've got, if we can prove that the inside angles add up to be 180, then we can prove that they are parallel, okay? So what can we see here? Well, we've got the obvious tangent and we've got an isosceles triangle. So straight away, I can see that this angle is the same as this one. So that's got to be 2 alpha. How does that help? Well, hopefully again, if you're now using the tangent theorem, tangent chord theorem, this angle has to be the same as this one. So that would also be 2 alpha, and hey presto, we've got alternate angles. Bang, done. But you've got to write stuff down. You've got to look at the clues that are in the question that you have and match up your parallel and circle theorems to see which ones are going to help. So the bisector part didn't really play anything in this role apart from saying that that line met there at D. So we can say that angle ACB equals 2 alpha. I could have just called that whole angle alpha for all we care, but anyway. And that equals angle ABC And why was that? Because we had an isosceles triangle. And we also have angle DAB equals angle ACB, which was 2 alpha. And why was that? That was the tangent chord theorem. Okay, so therefore angle DAB equals angle AB or ABC, which means that AD is parallel to BC because of alternate angles. Sweet.